Advanced Heat Transfer Module 1. There is a subfield in most engineering disciplines, typically in the field of mechanical, chemical, and material science engineering, called the thermal sciences. Thermal sciences includes the study of thermodynamics and heat transfer. Heat transfer is usually treated as a supplement to thermodynamic analysis and is usually treated as a completely different field. The main difference lies in the fact that in thermodynamics, most of the systems that are being considered is under equilibrium. In heat transfer, on the other hand, it deals with system in transitions. It provides additional laws for predicting time rates of energy transfer. Before we begin discussing the supplemental laws in heat transfer, we will first revisit the different conservation laws that hold true for any system in analysis. There are three conservation laws that are often associated with thermal science analysis. The first one is the law of conservation of mass. Second is the law of conservation of energy. And last is the law of conservation of momentum. These conservation laws are statements based from globally accepted truths that despite undergoing processes, these quantities are conserved. The law of conservation of mass states that mass cannot be created nor destroyed during a process. With respect to the subject of heat transfer, this is often encountered in the application of the continuity equation for the processes that involves gases or liquids. Thus, conservation of mass principle is often known in the form of the continuity equation. The continuity equation can be described as the rate of mass going into a controlled volume minus the rate of mass going out of the controlled volume. And it is equal to the rate at which the mass is being accumulated in the controlled volume. The right-hand side of the equation can either be positive, negative, or zero, which is the case for steady-state scenarios. In steady-state scenarios, the rate of mass going into the controlled volume is equal to the rate of mass going out of the controlled volume. Do recall that the mass flow rate is equal to the product of the density, the area, and the average normal velocity to which the flow is occurring. Like in many other cases, examination can be done at an infinitesimally small level and could be extended to multiple dimensions and coordinate systems. Next, we talk about the law of conservation of energy. Conservation of energy is given explicitly by the first law of thermodynamics, where it is stated that energy can neither be created nor destroyed during a process, but energy forms can change. Energies can exist in the forms such as kinetic, potential, electrical, thermal, chemical energy, to name a few. Also, do recall that heat and mechanical work is energy in transit. The law of conservation of energy tells that the total energy entering the system minus the total energy leaving the system is equal to the change of the total energy in the system. It can also be expressed in rate form, where the rate of energy going into the system minus the rate of energy leaving the system in the form of heat, work, and energy transferred via mass is equal to the rate of change in the forms of energies within the system. For heat transfer problems, the energy balance is converted into a form that highlights the amount of heat going in and out of a system and the changes in thermal energy of the system. This balance is written as the amount of heat going in minus the amount of heat going out plus the amount of heat being generated within the system, which is equal to the change of the thermal energy of the system. This is the starting point for most heat transfer analysis. Last, is the law of conservation of momentum, which is derived from Newton's law of second motion. Some references further expound this as linear momentum and angular momentum. In heat transfer, this is commonly used in the analysis of convection and mass transfer systems. More specifically, this is to analyze differential control volume elements. We further define body and surface forces, where the body force is the force that the controlled volume experiences, and the surface force is the force that acts on the surfaces of the controlled volume. Using Newton's second law of motion, the law of conservation of momentum can be expressed as the product of the mass times its acceleration on the different component directions, and it is equal to the total of the net body force on the different component directions plus the total of the net surface forces on the different component directions. Simply stated, the law of conservation of momentum relates the momentum possessed by an object to how much force it can exert on a body or on the surface. On the context of heat transfer, this is relevant for convection systems simply because the momentum possessed by a fluid in motion is used to drive the fluid, and the force interaction that results with the surface and fluid results to frictional losses that is simply converted into heat. We will revisit this in our in-depth convective heat transfer discussions. These three fundamental laws that we have discussed is the foundation for most concepts in our upcoming heat transfer discussions. Though simple, understanding them by heart can go a long way. In the next video, we will continue revisiting the different heat transfer modes you had probably learned in your undergraduate courses.